So here I was saying that the voltage is, if the current is 220 ampere, voltage is 440 volt. Okay. Or this is the output current, mean IDC. So we have to calculate mu and the DC output voltage VD for delay angle of 15 degrees. So we know that X is 0.3 ohm and E line to line is 440 volt. ID is to 20 ampere. This ID is equal to IDR is equal to IDC is equal to IDI. Okay, alpha is 15 and VD naught is given by 3 root 2 upon pi into ELI. So VD naught is 594.42 volts. This is VD naught. So you know that commutation resistance reactance, if commutation reactance is XC, so commutation resistance will be 3x XC by pi. So this will give me commutation resistance equal to 0.286 ohm. Equivalent commutation resistance. Okay. So ID is given by the formula root 3 EM divided by twice omega LC cos alpha minus cos delta. So if I know that VD naught is equal to 3 root 3 EM upon pi and omega L, so this is omega L, LC naught, it is omega, and omega L is nothing but XC. 2 pi FL is equal to XC. So, and I know that XC is equal to RC into pi by 3. So I will get omega is equal to RC into pi by 3. Okay. So using these two equations, this and this, okay, and by using this omega L equal to RC pi by 3, I will get ID is equal to VD naught upon twice RC cos of alpha minus cos of delta. No, I know alpha, but I don't know delta. What is delta? But I know what is ID. ID is 220 and I know VD naught from here. So I can calculate cos delta from this equation. Okay. So once I calculated cos delta, taking inverse of cos delta, I will get delta. Delta is coming out to be 41.05 degrees. Okay. Now you know that overlap angle is mu is nothing but delta minus alpha. So delta minus alpha is given by here 26.05 degree. So I have delta here, I have alpha here. I have calculated the overlap angle, that is 26.05. Now I will calculate this output voltage. For calculating output voltage, I don't need this mu. I can calculate it directly from alpha, this delta. But still, it was asked in the question to calculate the commutation angle. So output voltage is given by VD naught by 2 cos of alpha plus cos of delta. So VD is given by 511.02 volt, which is nothing but VDR, 511.02 volt. So this was the second problem. Now the third problem. Now this problem is related to inverter. Okay. So the problem is like, again we have a three-phase inverter with commutation reactance of 100 ohm, means XCI is 100 ohm. The current and the voltage at the DC side are 950 ampere IDC, and voltage at the DC side means VDOI. Okay, VDOI is given, sorry, 425 volt is the voltage on the DC side. It is 425. Yes, it is VDI means on the DC side 950 ampere means IDC is 950 ampere and VDI is 245 kilovolt respectively. This is on the DC side now. Then I have inverter, then I will have on the AC side. The AC line voltage is 325 kilovolt. Okay. Now we have to calculate the extinction angle and overlap angle. So what is given to us? XCI, equivalent commutation reactance of inverter, VDI, voltage on the DC side of the inverter 245 kilovolt, IDC 950 ampere, and V line to line for inverter is 325 kilovolt. This is on the AC side. So for inverter we know that VD naught for the inverter is given by 3 root 2 upon pi E line to line for the inverter, which is equal to 3 root 2 upon pi. What is E line to line? 325. So VDOI is 439 kilovolt. We know that VDI is equal to VD naught I cos gamma minus RC into IDC. RC is nothing but 3 upon pi into XCI. So we know that VDI, the voltage on the DC side, is 245 kilovolt. So converting it into volt, VDOI is 439. We calculated it. 439 converting into volts into cos of gamma minus 3 upon pi XC into IDC. So we are getting cos gamma here equal to 0.7648 and gamma equal to 40.1 degree. Okay, so this is the extinction angle gamma, which is equal to 40.1 degree. Now we have to calculate the overlap angle as well. Okay, overlap angle means we have to calculate mu now. So let us use the formula VDI is equal to VDOI by 2 cos beta plus cos gamma for inverter. Okay, so which is equal to VDOI upon 2 cos beta is nothing but gamma plus mu plus cos of gamma. Okay, and cos gamma is 40.8, so cos of gamma is nothing but 0.7648. Substituting it here, from here I will get cos of gamma plus mu. Cos of gamma plus mu will be equal to 0.3515, and taking inverse I will get gamma plus mu is equal to 69.4 degree, but I have to calculate mu and I know gamma is 40.1, so mu will be equal to 69.4 minus 40.1, which will come out equal to 29.3 degrees. So these were the few problems that numerical problems related to this HVDC system, both inverter and rectifier. So let us discuss about the DC circuit breaker. Okay, so these DC circuit breakers, they are actually based on the commutation principle, and commutation principle, by using commutation principle, what we are doing, we are creating artificial current zero. Okay, in case of AC, we have the natural current zero, but in DC we don't have a natural current zero. So what we are doing, we are using the commutating circuit, which will give artificial current zero. Okay, so we know that in AC system, any faults or abnormal conditions, they will cause tripping of the circuit breaker. Okay, the relays will sense and they will trip the circuit breaker. However, in DC, circuit breakers are not mandatory. Even though we can control the fault or overcurrent or over voltages by controlling the converters. Okay, by controlling the firing of the converters. Still, these circuit breakers are needed in HVDC as a backup. Okay, so HVDC circuits of medium, we have medium, low, and high switching energy. So HVDC for these are based on artificial current zero principle. Artificial current zero principle means we are forcing this is IDC, constant current. We are forcing this current to go to zero like this. And at one of the current zeros, artificial current zero, we will trip on the circuit breaker. So this artificial current zero, these are created by using a commutating circuit, which consists of an LC circuit with large capacitor bank. Okay, and this LC circuit with large capacity, it is connected in parallel with the DC circuit breaker pole. Okay, so this current, it will oscillate for few cycles. Okay, for few current zero, and the main circuit breaker pole interrupts the current at one of these current zeros, artificial current zeros. Okay, so the circuit will be slightly like this. I'm telling you that this is a commutating circuit or commutation circuit. So I am saying this is my main circuit breaker, and I am using a LC circuit. This is L, this is C circuit of a large capacity in parallel with the main pole of the circuit breaker. Okay, and what will happen, using this principle, the current will be reduced to zero. This current will be, main current will be reduced to zero. Okay, like this for few cycles, I say. And what we will do, we will operate this circuit breaker at one of these current zeros. These are artificial current zeros. Okay, so here I am saying that, however, the commutation principle giving artificial current zeros have been successfully applied for medium and low switching energy DC switching devices in two-terminal DC system. Means we have used this commutating circuit for two-terminal. Maximum, I told you, we have maximum three-terminal HVDC system. We don't have more than three-terminal HVDC system in the world because it increases the complexity. So for medium and low energy switching energy systems, this artificial current zero technique has been, or commutation principle has been tested. Okay, in case of a two-terminal HVDC system only. So you know that in case of AC, the contacts of the circuit breaker, they are separated from each other. As they are separated from each other, an arc is developed, and this arc is quenched by the arc quenching medium like SF6 or vacuum circuit breaker when the current passes through the 0 point. which is called as the natural current zero point of the system. However, in DC circuit breaker, we know there is no zero current. And also in DC, energy in the system inductance is high. Okay, the system energy in the system inductance is high, which is given by 0.5 L into I square. We know that I is very high. We have an inductor of large size, so huge energy is stored in this inductor. And arc with such high energy level cannot be interrupted by simple circuit breaker. Means simple air, vacuum or SF6 circuit breaker cannot be interrupted because the current is at constant value. Moreover, the system inductance has a very high energy, which is given by half of Li square. Okay, so if we will try to suppress the, we cannot suppress the arc by interrupting. We cannot interrupt the arc, or we cannot interrupt the current by using circuit breakers. Okay, here. So what we need here, we need some devices that will reduce this current to zero. Okay, and this is done by using some commutating circuit. Okay, so what is here it is saying how this circuit is working actually. So the breaking of truly HVDC circuit is difficult due to the non-availability of the natural current zero and high stored energy in the smoothing reactor. Okay, high energy in the smoothing reactor and absence of natural current zero, it is difficult to break the HVDC circuit. Okay, so when the contacts are separated, an arc is drawn here. Okay, so what will happen, we are using here a pre-charged capacitor. The moment the arc is drawn here, what will we do? The energy in the series reactor should be dissipated for interrupting the arc current. Okay, the DC arc will continue to burn till the energy in the circuit is not completely dissipated in the heat of the arc. Okay, so this energy is so large that it can break the circuit breaker contacts or damage the circuit breaker contacts, and it may destroy this the circuit breaker contacts while interrupting the current. So what we have to do, we have to make some artificial current zero. Okay, and this is the technique for doing the artificial current zero. So this is the main circuit breaker, this is the LC circuit, and here we have this switch which is called as 5. Okay, so this is the commutation principle. This figure will consist of 3 main components. The first is main circuit. Main circuit means 1 and 6. It consists of a circuit breaker, main circuit breaker, which carries current IDC. Okay, and commutates the current to the commutating circuit. This is the commutating circuit here, down here. Now the commutating circuit consists of inductor, capacitor, and this switch here. Okay, now this second, it is the current energy dissipation circuit, which dissipates or absorbs the energy, which is this circuit is made of zinc oxide arrestor, which absorbs some of the energy of the system. Okay, so this commutating circuit, it may be active commutating circuit or a passive commutating circuit. In case of active commutating circuit, active components such as pre-charged capacitor, means this capacitor is initially charged, and spark gap, pre-charge capacitor is 5, and this spark gap, this is called as spark gap, is used. Such a circuit is called as active commutating circuit. So the this is pre-charge capacitor and spark gap. So in case of a passive commutating circuit, we have an LC resonant series circuit without active components. Like we don't have charge capacitor here in case of passive commutating circuit. Okay, so you know, if direct current, this 6, you have 6, which is mentioned by 6, this inductor, it represents the DC current transformer for measurement of current. It measures the current. So energy absorber 2, it will limit the transient recovery voltage across the breaker, and it will absorb the energy in the main circuit. Okay, so zinc oxide surge absorbers have higher energy absorption capacity and precise protection level. That's why zinc oxide surge absorbers are used here. That is this 2, it is zinc oxide surge absorber. So what is happening? Immediately after opening the contacts of the main breaker, circuit 1, this vacuum gap, it triggers. Okay, at time t is equal to t naught, it triggers. Now this pre-charged capacitor, no, the moment it triggers, this is short circuit, means at that time. So it will be positive at that time, this will be negative. It will discharge through this path. The capacitor will discharge through this path. So this discharge current, it will flow in opposition to the IDC, main current. So what will happen? This discharge current, which is flowing opposition to the IDC, it will reduce the magnitude of the IDC current. Here, like this is IDC. So what we are, a current is flowing which is opposing to this IDC. So the magnitude of the IDC will reduce like this. So now when it will reach 0, at one of the current 0, we will turn on the circuit breaker. Here is the IDC in the main circuit, it drops down and oscillates with several current zeros. So these current zeros are created due to arcing state in the main contacts space of the circuit breaker. Now the main current is interrupted by circuit breaker at one of the current zeros. After that, valve gap opens. When this circuit breaker is operated at one of the current zeros, this valve gap again opens. Okay, means this valve again will open, and this will be open circuit here. So no current will flow through this now. So the valve gap again opens and commutating circuit gets open, means commutating circuit will get open. So last, finally, current 0 in 1 will produce high transient recovery voltage across the circuit breaker. Okay, so and the energy in the main circuit, this is LD 1 by 2 L I square. And the energy in the main circuit, it must be absorbed to limit the transient recovery voltage to safe value. Okay, so this energy must be absorbed so that transient recovery voltage should remain within the safe limit. So this energy is absorbed partially by capacitor. That energy is absorbed partially by capacitor and partially by the inductor. Okay, because these are the energy storing devices. Okay, so the magnitude of this transient recovery voltage, it depends upon the time of interruption and voltage at that time. What is the voltage across the system at that time? So this was all about this these two topics, that numericals and this DC circuit breaker. So I will circulate the notes of this circuit breaker as well. So in case you feel any problem, so you can contact me. Thank you very much.